Hello again. Please watch first video if you didn't watch, because I am not explaining as detailed as in the first video, to be quick. Also, I am not solving the first question because that's exactly the same in the first videos one. Just the difference is axis goes 1 to 7, not 1 to 6. That's not an important deal. So, the first question now is, the number of telephone calls that arrive at a phone exchange is often modeled as Poisson random variable. Assume that average there are 7 calls per hour. What's the probability that there are exactly 4 calls in 1 hour? Okay, what's the probability that there are at most 6 calls in 1 hour in 30 minutes? Sorry. Xt number of calls in t time unit t. Okay. Lambda is equal 7. Lambda is equal 7 calls. 7 calls per hour. Okay. What are you asked? What are we asked? We are asked for 1 hour again. So time unit is 1. Lambda 1 is equal 7 again. For first question, first part A. What's the probability that there are exactly 4 calls in 1 hour? Exactly 4 calls means, firstly, xt is distributed as Poisson with lambda equals, x is distributed as Poisson with lambda equals 7, xt de lambda equals 7 times t. I explained it more clear in the last videos. I just tried. So, exactly 4, yes. Probability x is equal 4, that's equal e to the power minus lambda. What's lambda? 7. Lambda 1 is 7. Yes. Times 7 to the power 4 over 4 factorial, right? Exactly 4 calls. That's the probability. Now, what's the probability that there are at most 6 calls in 30 minutes? The important thing is that the important thing of this part is now t is 30 minutes. I mean 30 minutes is one half of 30 minutes is one half of an hour, so t is equal 0.5. Lambda 0.5 is equal 0.5 times 7, that's equal 3.5. So new lambda is 3.5. At most 6 calls is much. I have tried other ways, but I can't find. We have some there. Probability x is greater than or equal to 6 at most, right? Yes. That's equal probability x is equal 1 plus probability x is equal 2 plus probability x is equal 3 plus probability x is equal 4, probability x is equal 5, and probability x is equal 6, 1 to the 6. Now we open that, e to the power minus 3.5 times, that's lambda, new lambda, 3.5 to the power 1 over 1 factorial plus e to the power minus 3.5 times 3.5 to the power 2 over 2 factorial plus e to the power minus 3.5 times 3.5 to the power 3 over 3 factorial plus, like was that, finally e to the power minus lambda times lambda to the power 6 over 6 factorial. I add them to each other. I can't find another way. I can also try 1 minus x is greater than 6, and it goes infinity. I try to get Taylor series, but I can't, so I sum them. That's equal, numerical value of this is equal 0. Close them. You can calculate it. I did already. Second question. Second question. An AC machine is designed to operate properly with power voltage settings between 103 and 161. The voltage setting is uniformly distributed. Determine the mean variance of the voltage settings. X value of voltage. Is outcome. So X is distributed as uniform. A equals 103 and B equals, what is it? 161. Because I already explained in this video, but 100, 103, 104, 105, 161, 160, 161. It goes numbers A plus 1 to the B, and it's discrete uniform distribution. Determine the mean and variance. For mean again, first, how many terms we have firstly? Last term minus first term plus 1. That's equals 59. Yes, 59. 59th term. So we have 59 term. We have 59 term, yes. Sometimes I confuse while I am calculating means. 59 term, okay. That's equal 29th term. That's equal 13th term. I'm writing it there. 29th term. That's equal 31st term. 29th term there. Here is mean, and 29th term is here too. Sum of them 58, and with the 13th term, the total number of terms is 59. So to do that, first term is 103, mean is small x, last term is 161. X minus 103 plus 1, number of terms, is equal 30. There are 30 terms like that. X, which is mean, is equal to yes, that's the mean, right? I'm checking. Yes, that's correct. That's mean. And variance of the voltage settings. What is variance of a discrete uniform series? Vx is equal b minus a. B is 161 minus 103 plus 1. That's number of terms actually. Minus 1 over 12 That's equal 290. Okay, second question is done. Third. Okay. There is 230 liver cancer patient in an hospital. Probability of patient dying following here is 6%. What's the probability that exactly 3% dies following year? Calculate the expected death. X again. X is most practical for me. Practical one for me. Number of patients died because of cancer in that hospital, specified hospital. I'm not writing too much now. What's the probability that exactly 3% dies? Exactly 3% dies, okay. Right. I just checked something. X is distributed as binomial. Why? We have 230 trials. They are people, patients, and they will die with probability 0.06. So X is distributed as binomial, and to calculate probability, X is equal to 3, right? Exactly 3. Yes. X is equal to 3 is 230 chooses 3 times 0.06 to the power 3 times 1 minus p to the power remains. Yes. When we calculate it, we will find a number. I don't write it now. You can try. Yes. Okay. Any question? Calculate the expected death. Hence, X is distributed as a binomial. Expected value of binomial is n times p. Expected value of binomial is n times p. N is equal 230, p is equal 0.06. We can calculate. The probability that, okay, new question. The probability that a wafer contains a large particle of contamination is 0.03. It's assumed that the wafers are independent. What's the probability that 5 large particles detected after analyzing 320 wafers? Contamination is a kind of defect. So, when we define X number of defected wafers, and whatever, X is distributed as negative binomial. The parameter R is equal 5 and P is equal 0.03. Because we are looking fifth success is finding the defective one. We are looking fifth success with probability 0.03 in 320 trials. So, probability x is equal 320 is this. X minus r chooses how many? R is 5, right? 320 minus 5 chooses r minus 1. 5 minus 1, that's it. 0.03 to the power r is 5 times 1 minus 0.03 to the power x minus r remains. I already explained in detail, I guess, in the last video. You can check. When we calculate them, you will find the result. That's numerically long language. Okay, that's all. Last two questions. A class consists of, what's the expected number of wafers analyzed until the fifth large particle detected? Sorry for that. One part of the question. Expected. X is distributed as negative binomial with parameter r equals 5 and p equals 0.03. So, expected value of negative binomial is, what is that? R over P, right? R is 5 over 0.03 expected as, that's equal, like that. They are 6. Okay, I'm deleting now. No more parts. The class consists of 42 students, 14 of the students decide A for the final. 7 students are selected at random from this group. What's the probability that at least 7 students selected recite at least 7 students A for the final exam? What's the probability that 2 of that part is not writing? Yes. One of 7 students, sorry. At least one of 7 students, okay. We are choosing, you can also read questions on yourself too. X is number of students get A. Let's probably this one of 7 students. Okay. X is distributed as hypergeometric with parameter k is equal 14, capital N is equal 42, n is equal, small n is equal 7, because we are choosing finite number of item trial from selected one among a population. So it's hypergeometric. At least one of 7 students. So probability X is greater than or equal to 1. That's also equal 1 minus probability x is equal 0, because at least one of students means we have no students in this group who gets A. Sum of all of probabilities is 1, and this is expressed like that. I already explained details in the video before. I mentioned that in the first question. Yes, first question. Okay, so 1 minus hypergeometric 14 chooses 1, k chooses x times capital N minus 14 remains students chooses small n minus x. Students that will be chosen remains over favorable outcomes over possible outcomes. 42 chooses. Sorry. Yes, I am right. 40 chooses 7. Sometimes it might be confused and doing with naive might be hard. I know formulas well, I think, but sometimes I can confuse too. I already solved too many questions. So you can calculate this. That's equal 0.96 closer. Last question. The problem that's the same. No, not the same. Things the wafer question. X number of defecteds, and it's assumed that wafers are independent, yes, like in the question. What is the probability that exactly 140 wafers need to be analyzed before a large particle is defected? Okay. This 0.03. A large particle is detected. What's the exact number of analyzed wafers? Okay. We are analyzing them until we get the defected one. Detected also, sorry. Detected, sorry for typo. Detected one. We are analyzing them until we get the detected one. Finding a detected one is success, and we are trying until we get first success. So, X is distributed as geometric with parameter P is equal 0.03. Find probability of finding the detected one. So, probability X is equal 140 is equal to P times 1 minus P to the power X minus 1. Yes. I already explained the geometric distribution question in the last video. I am not doing that again. 0.03 times that's equal a number, long number. What is the expected number of analyzed wafers until large particle is detected. Large particle is detected. Expected value of geometry is 1 over p. I'm checking. Yes, it's 1 over p. So p is 0.03. Expected x is equal 1 over 0.03. That's equals 33 to the power 3. That's all. I hope it's also helpful too. I am mentioning again, you need to watch first video if you don't get clearly. Thanks for listening and watching.